And as you probably know, DreamWorks is not Pixar. So it's these characters here. This is an overview of the different departments, the pipeline we call it in the movie industry. The different departments that a movie goes through. As you can see, it's very complicated. They each represent a little task in this pipe. And I am involved, or actually I'm managing two of these, or the research and development in two of them, namely the effects one, which is typically things like fire, smoke, explosion, stuff like that. And then the other one called C effects. And C effects are effects associated with characters, so cloth and hair. But the common denominator is, a lot of this is based on physics. So simulating natural phenomenon either associated with nature or characters. And we do a lot of research in these areas. This is a breakdown. I'm sort of trying to build up. This is a breakdown of some of the types of effects associated with movies we did between 2010 and 13. And the really interesting thing is, if you start looking at what's underneath, it turns out, I'll explain, by the way, what hero effects is. I'll give an example of that. But it basically means one-off. But it turns out that a very big portion of these effects are volumetric. If we go back again, you can see we have fire, smoke, liquids, and clouds. Obviously, that's a volume, right? But it turns out even the remaining stuff, the hero effects and the destruction, is typically partially volumetric. So the takeaway message is a lot of what we do is based on volumes. So volumes are incredibly important in movie production, especially in effects. So that's sort of the segue into the main topic of the talk, which is this thing called OpenVDB. And OpenVDB it's a volume format that won an Academy Award earlier this year. And this is a very simple breakdown of what it is and why it's interesting. So VDB is both compact and fast. And it turns out it's fairly easy to write a data structure that's compact. It's also fairly easy to write a data structure that's fast, but it's very difficult to write one that's both. And that's the claim here. It's compact because it has very little overhead. So basically, you're paying the price for the important information you put into the data structure and not a lot of overhead. It's also compact because it's adaptive. So it actually adapts to the data or the effect, like a smoke that's moving around. It's fast because it's what we call a shallow tree. I'll explain a little bit what that really means. And it's also fast because we can do something called inverse tree traversal. So a few highlights. So VDB is unbounded, which is kind of a strange thing. Most of the time when we're dealing with volumes, we have a box, like a virtual box in which we sort of do our thing, like our simulation or cloud or whatever it is. VDB has no box. You can literally set values anywhere in index space, and you can probe for values anywhere in index space, which turns out to be very useful when you're doing effects, because oftentimes when you're setting up a fluid simulation, you have no idea where the fluid is going. So if you have a box, chances are you're going to hit the edge of the box and you have to resize it, which can be very expensive. Or you're oversizing it, so you're paying too much memory overhead up front. So that's nice. It's also compact, as I said. It's both compact in memory, but also on disk. It's fast, which in computer science terms means it's constant, meaning it's independent of how much stuff you put in it. You don't want it to get slower the more information you shuffle into the data structure. And it actually achieves that. It's fast for what we call random access. So random access means you ask for a value anywhere in index space, or you insert a value anywhere in index space. That's in contrast to what we call sequential access. Sequential access means, let's assume you have a volume already and you want to do something with it. You want to massage the values, like you want to solve an equation or filter it or something. And now you actually just want to visit all the value as fast as you can. We call that sequential access. And sequential access is usually faster than random access, but you have to be careful because it's difficult to both have optimal random and sequential access, and VDB actually achieves that. I'll explain how.
What's the difference between a voxel and a node iterator?
So a voxel iterator is an iterator that visits the voxels, like the actual values. A node iterator is one that visits the nodes in the tree. So it's a very good.
In the internal tree that represents.
Exactly. So a voxel iterator is often composed of node iterators. So it's internally actually uses a node iterator. It has fast I/O, and it has, this is pretty nice, it has a built-in acceleration tree. So oftentimes when we do things with volumes like ray tracing or collision detection or something, we have to build an acceleration tree to accelerate, let's say the rematching. Because VDB is already a tree, it already has that built in. So there's no overhead of producing that. And then we can use it for many different types. So VDB or OpenVDB has sort of been my pet project for many, many years, probably too many, to be honest. It's almost embarrassing now that I sort of look at the whole scheme. So the two first ones were done with some PhD students of mine. But the last three ones, so they were done in academia. So the DT grid and HRLE. The DB grid was when I left academia and went into the movie industry, I immediately thought, oh, I know how to do this. We're doing Pirates of Caribbean, the third one. And they asked me to help them with some fluid sims. And they said, we have problems with memory. Like, do you have a tool? Do you have a data structure we can use? And I said, oh yeah, we can use DT grid. It's awesome. And it quickly turned out to be not awesome at all, because it solved one very specific problem. And in movie context, it's not enough that you can solve one problem really well. You have to be able to solve many different problems. So the fact that we could do fluid sims was great, but we couldn't use it for rendering. So I sort of only solved half of the problem. So that's why I started on this new thing called the DB grid. And that eventually evolved, became VDB, and then two other people got involved, and it was open sourced as OpenVDB in 2012. So the really nice thing about OpenVDB and the open sourcing is a lot of commercial companies picked it up. That's actually why DreamWorks agreed to open source it. So Houdini makes a software package that is used throughout the whole movie industry for visual effects. Maya, of course, also uses it, and then a lot of the renderers. And then since we released it in 2012, it's actually been used in more than 70 different movies. Most of them actually not done at DreamWorks. So we collaborate a lot with other studios. Like Pixar uses it too. And a lot of live action studios use it as well. So a little bit of terminology. So voxels, of course, as I'm sure most of you know, it's abbreviation of volume and pixel. So it's a 3D pixel element. And it's sort of the smallest addressable space in this volume index space. Then we have, this is unique to VDB, we have tiles. And tiles you can think of as megavoxels. They're very big regions in index space, and they live higher up in the tree. So they represent large constant regions. And then the last one is completely unique to VDB, which is every value that we put in, we can associate with a binary state. Meaning it's either an active value or an inactive value. And the interpretation of that is completely application dependent. It depends on what you're interested in. So, but often it means this value is interesting or this value is not interesting. And it turns out to be an extremely...
Is it a single bit, or do you have a bit mask?
No, that's right, it's a single bit.
One bit?
Yes, you'll see exactly how that's done. So this is the sort of the underlying data structure. It's called VDB, and it's kind of strange. It's inspired by, but it's not the same as something called a B+ tree. But what really characterizes it is it's a very shallow tree. So the path from root to leaf, so the root is, of course, the top node. The leaf nodes are the blue ones. It's very shallow. and it's actually fixed depth. It's always, in this case, 4. We can configure it to any configuration, but it turned out this was the best one that I've experimented with over many years. So the root node is the only node that is actually dynamic and sparse. It can resize itself. That typically means that it's slow, because resizing comes at a cost. All the other nodes have a fixed size. But as you can see, the fan-out factor is high in the beginning, and then they get smaller and smaller. And this is very unique. And the reason that they're very, very high in the beginning is you wanted to cover a huge index space. So why does it look like this? And there are many different ways of sort of interpreting this. One of my favorite analogies is actually when you look at a modern CPU. A modern CPU is, as you probably know, has this very complicated memory hierarchy. So we have what we call caches, basically. So we have a fixed amount of cache levels, and they are increasingly faster, but also smaller as closer we get to the computational core. So L1 is very small, but incredibly fast. And then you go up, and eventually you have the RAM. And the RAM is very slow, but it's dynamic. And it's exactly the same idea in VDB. So the question is, how do you program for something like this? It's a very complicated memory layout. Well, there's a kind of a class of algorithms called cache oblivious algorithms. And the underlying idea is super simple. You take your workload and you divide it until it fits in the various cache levels. And when you do that, guess what? You end up with something that mimics the VDB tree. So this is an example of one of these trees. It's a wire rendering. And so let's see. I think the green ones, you're not seeing the root node, because the root node is infinitely large. But the green ones are the nodes just below the root, and the orange ones are the level below it, and the blue ones are the leaf nodes. So the leaf nodes, in this case, are very small. They're just 4 by 4. But as you can see, the fan-out factor grows dramatically. And this is an example. We took one of the characters from one of the Dragon movies and turned it into this thing called a level set. Level set is just a distance field, basically. But it's a narrow band, so we only have information in close proximity of the surface. So it's what we call a sparse volume. And this would take about 1/4 terabyte using existing techniques. But with VDB, it's less than 1 gigabyte. So it's a huge memory savings, of course. So this is to sort of answer your question about the bitmask stuff. It turns out bitmask plays a central role in VDB. And they're a very simple concept, but it turns out they can be used for many different things. So the simplest one is exactly what you said. So let's suppose I told you that each of the nodes are dense, the ones below the root node. So let's suppose I'm in a leaf node, and I'm putting in values now. And somehow I want to indicate that these values are interesting. I want to be able to skip everything that isn't blue. Because if let's say I want to massage the values, if I had to go through all of them, it would be very slow. So I want to be able to sort of filter them out. Of course, the simplest way to sort of set a state is just using a bitmask. It's a super simple idea. But it has way more applications. Another application is that the bits, you can actually think of the bits as storing the topology. So we are not anywhere in the data structure storing the actual coordinates, x, y, and z, because they're implicitly encoded in the bit string. And the way to think about it is, if I'm giving an offset, I can actually produce the corresponding x, y, and z coordinates through these very strange operations. But the really cool thing is that most of these operations that I have are actually, when you compile the code, this is all that you actually do at runtime. And these are very cheap bitwise operations. So basically you're shifting to the right, you're doing bitwise and that's pretty much it. Yes?
How, because you've encoded coordinate, you've encoded geometry in this fashion,
Right.
how
That's a very good question. Arguably, this can generalize to any dimension, but I think it has a very unfavorable scaling when you go above 4 dimensions.
4?
Yeah, yeah. I've done it in 2. Obviously, we use it in 3 all the time. 4, I think you can do it, but I think the overhead, the overhead of having these dense nodes is really going to bite you. There's a ton of metaprogramming in this. There's a ton of metaprogramming. That's actually, that's sort of the secret sauce.
So, the level 4
Mm-hmm.
is basically when you need to render things specifically in a high resolution area that has a lot of variability.
Right.
And so you just, and what's your algorithm for deciding what the variability is?
That's an oracle that lives in the application. Because it's not, it really depends on what you're doing. So we can't build that in, because obviously different applications have different.
Like a roughness factor or something where
Sure.
So that's what we're talking about for this. The data structure will accept whatever level of granularity the application says it needs.
Exactly. That's exactly right. These were sort of 2 obvious applications of the bitmask. One is to just indicate which one are interesting. The other one is to implicitly store the coordinates. But there's some other ones that are even less obvious, but even more important. The other one is when we want to do sequential access. As I mentioned before, sequential access means just visit all the values that you put in the data structure that you indicated as interesting as fast as you can. The naive approach, of course, is to go through the bitmask and check, is this bit on or off? Is this bit on and off? Is this bit on and off? We can do better than that. We can actually take the bitmask, separate it in words. This is just, I'm just illustrating with 8-bit words, but of course in modern computers it's a 64-bit word. And for each of these words, we can very quickly find the least significant bit. We can actually do it in what's called an O1 operation. And we can prune words that have nothing in it with a single operation. So we can very quickly march forward. Another very nice feature is we can use the bitmask for compression. Right? So when we write stuff out to disk, if we know, and there are many applications where this is the case, if we know what an inactive value corresponds to, often that's the background value. When we write it out to disk, we're using the bitmask as sort of the compression key, the codex key. And we're only writing out the active values. So there's a tremendous file footprint savings.
And you have one bit mask for whatever sets of potentially vector values you're storing per cell. Right?
Or you can have more. You can actually have more than one bit mask. So there are some applications where we use more than one. So for level sets is a narrowband level sets is an example where you typically use 2. You have one that is outside and one that's inside. There's another one here that turned out to be very useful, which is, suppose we have 2 grids, and I want to do the union of the grids. Turns out you can do that incredibly efficiently using these bitmasks, because you're just doing a single OR, which is, as you probably can imagine, incredibly fast. You can also do intersections, just replacing it with an AND. Or you can do differences. And we do this a lot. Now this is my favorite one, and this is very important for level sets in particular, or interface tracking. It turns out we can also use it for something called a morphological operation. So I'm illustrating this now in 2 dimensions. So imagine that we have 8 by 8 grid, and we have set some pixels. And now I want to dilate this set. Dilating means I want to add all the neighbors, giving some kind of dilation algorithm, which is, in this case, I'm just going to say it's going to be neighbors in X and Y. Now, the naive way to do it is to use an iterator, find each of the purple pixels, and just make sure you set the bit of each of them. But we can do much better than that. Because the bitmask, in this 2D example, is represented by a word. Each row, each column has a word associated with it. And it turns out to dilate this set, it translates to some very simple bit operations. So if we look at the row with the arrow, all I have to do is I have to take the word of that row and OR it with the one above it and the one below it, and then left and right shift it and OR it with itself. If I do that, I've actually set these bits, which is incredibly fast to do. And you can apply this algorithm to, obviously, each of the rows, and suddenly you've dilated the set. So this is very useful when you do interface tracking, when you have a level set that moves, and you want to make sure that the level set follows it as it moves in space. And of course, you can do the same thing with a erosion. You just use different operations. Now, instead of an OR, you do a bitwise AND. And then you can erode it. OK, so there's one more sort of nerdy detail about this data structure, which is access. So I said it has fast access. And why is that? So let's talk about random access. So random access really just means, given an x, y, and a z, give me the value back. So how do we do that? Well, in most tree data structures, what we do is we pass the x, y, and z to the root node, and then we do a tree traversal. OK, so that's pretty obvious. And in this case, the value turns out to be associated with a leaf node, and we return the value. Now, the good news is, because we have a fixed depth, it's always 4, right? It can never be more complicated than traversing all the way from root to leaf, which is constant time. That's the good news. The bad news is we still have to go through 4 levels. So it turns out we can actually do better. But these are the operations that the computer does when you do this traversal. And it looks like gibberish. But there are actually some very interesting observations you can make. The first one is, when you compile the code, the green operations are the only ones that you execute in runtime. Everything else is actually compiled out. So there are very few operations. It's very fast to go down the tree, which is good news. Another very interesting observation you can make is, so these are the operations for the root node, all the internal nodes, and the leaf node. The other observation you can make is that the first thing you do with your x, y, and z is you do a bitwise AND. And that's super interesting, because it turns out bitwise AND is the only operation, bit operation, that is robust to signed indices. So it actually means that everything here works even when you give it negative coordinates, which is kind of cool. We haven't done anything, and yet we have a data structure where you can set values at minus a million, plus 100, minus a trillion, or whatever, as long as it's within the bit precision of your indices. So you get that for free. But the really cool thing is this. It turns out that the operation that you do at each of the levels of the tree start with the same thing. It's the same x, y, and z, which is at first maybe a little bit surprising, right? You'd think that you compute something at the root level, and then you pass it on to the next one, and then that processes it. Sort of a sequential operation. But it turns out it is not. It's actually the exact same x, y, and z that you input. And that's a consequence of the way that the tree is designed. So it's not a trivial thing. It's actually, yeah, it's not a trivial thing. But why is it exciting? It's exciting because it suddenly allows us to initiate this tree traversal anywhere. In particular, we can do the following, which is very nice. We can, instead of going from the root down, we can start anywhere. In particular, we can start at the leaf. So suppose we have this extra little structure called an accessor on the right. And what I'm going to do is I'm going to take the nodes from a previous access and put it into this structure. Okay? And then I'm going to associate, this is a hash table. I'm going to associate each entry with a hash key. The hash key looks a little bit strange, but the important thing is it's very fast to compute. It's just 3 bitwise ANDs. And the key uniquely determines if X, Y, and Z falls in a particular node. So here is the trick. The trick is, if you now want to know the value of another associated with another X, Y, and Z, instead of starting at the root, you're going through this table. And the first thing you're going to do is you're saying, giving X, Y, Z, let's compute the hash key. It's just 3 bitwise ANDs. And chances are, because of the way that we use these data structures, that you're going to end up in the same node. Because we call it random access, but it is never random access. In fact, you should never design your algorithm so you jump around in memory. That's the worst thing you could do, regardless of what data structure you have. So we call it random access, but in reality, it has a high degree of what we call spatial coherency. Think about like ray tracing. Ray tracing is an example people often mention when they want to talk about random access, because you don't know where the ray is coming from or where it's going. So you can't implement it in terms of iterators. But it's not spatially incoherent, right? Because as the ray marches through space, it's actually visiting neighbors all the time. So it's perfect for applications like that. Another example is finite differencing. You know, you suck in a value and the neighbors. Or filtering, same thing. So all of these applications have high degree of spatial coherency, meaning that we can now do, effectively what we're doing is we're doing bottom-up traversal. So we've inverted the tree traversal. So, which is really nice because it actually means that now the access is independent of the depth of the tree, on average. So now we have incredibly fast data retrieval. So this is actually sort of this one of the secrets to the performance of the VDB tree. So this is just illustrating. So what happens if I have a miss? Well, then I move on to the next entry in the table, and that might find the common ancestor. And now I'm only doing a partial traversal. Now I'm starting at an internal node and then moving down. Okay, so there's another analogy to this that I really like. It's from the world of CPUs. So as you saw before, the memory hierarchy in CPUs is pretty complicated. And you may wonder, how is that, how do you sort of shield that from the programmer? And of course, we've introduced this thing called virtual address space, which is think of it as a mapping between physical memory and virtual memory. And this mapping is actually implemented through a hardware cache. It was actually it's called the what's it called? TLB, sorry, translation look-aside buffer. And it was the first hardware cache that people implemented on CPUs, even before data caches, which is kind of interesting. And it accelerates this mapping between virtual space and physical space. And when you think about it, that's exactly what the accessor does in VDB. So it's an acceleration between these two different spaces. And of course, the analogy is in VDB, you're given an X, Y, and Z. You want to grab the value back. You have no idea where the value lives in the tree. But you cache previous mapping, which accelerates the subsequent lookups. So another nice thing about the VDB tree is, I promise you, I won't have much more. I'm almost done with the boring details here. It's a tree, right? So tree means that we have a built-in acceleration structure, which is very useful for many different things. We call it a BVH, bounding volume hierarchy. One cool thing is that you can process a whole branch instead of processing every single voxel, which means that we can do multi-threading very quickly. We can do things like Boolean operations on trees almost in real time. Because oftentimes, like when we do intersections between two surfaces, you're only interested in the values that are actually overlapping. The rest are just being copied. But instead of copying the values, you can now copy a whole tree branch, which is just copying a pointer. So that's incredibly fast. We can also do things like flood filling and sign propagation as a hierarchical operation, which is also very fast. And then, of course, we can do ray tracing. We can use the VDB tree structure to accelerate the ray marching. And And this is what I'm illustrating here. This is what I call a hierarchical DDA, or a DDA means a digital differential analyzer. And it's simply a way of taking a line and sort of, maybe you've heard about the thing called Bressenham's algorithm, which means given a line, how do you rasterize that onto a computer screen? Basically, what pixels do you have to turn on to represent the line? So it's sort of pixelizing a line. There's the same thing happens in 3D, which is, given an array, what voxels does the array go through? Now you can imagine that you can have one of these DDAs for every single level in the tree, which is what I'm trying to illustrate here. So it allows you to skip empty space incredibly fast. In this case, I'm marching very quickly through some of the higher level nodes until I hit a voxel that is close to the surface, in Bonnie in this case. And then I drop down one level, and now I start marching in voxel space instead. And you can play this game at all 4 levels, which means that you can incredibly fast. Let's say you're rendering a cloud landscape. Chances are you have empty space between the clouds. And you want to march as fast as you can. And this technique allows you to leapfrog. So VDB is open source as this thing called OpenVDB. And it's accompanied by a large tool set of all kinds of things that we found useful in movie production, but you can use it for many different things. So there are a lot of level set tools in there, finite difference libraries and ray tracing, and yeah, you should probably take a look at the website. I'm just highlighting a few of them. So one of the classical ways that we generate a volume is we have the model department generate polygonal surfaces. This is, it's called the, sorry? Yep, the crawler, that's right. It's a very high detailed model, has very small details in it. And it's notoriously difficult to take one of those and represent it as a volume, unless you can go very high resolution. And another problem is that oftentimes these models are what we call, they're not physically realizable. And what we really mean is it has either holes, it's a non-manifold surface. It has holes or self-intersections. And the cool thing about a level set is it cannot, by construction, represent anything that is not physically realizable, which is why it's perfect as a representation for 3D printers. Because the problem with the 3D printer is if you give it a model with self-intersections, what's the printer going to do? But the problem, of course, is how do you go from something that has self-intersections to something that can't represent a self-intersection? And we have that problem all the time, because when the modelers generate something, they don't care about whether it's physically realizable or not. They just care about what it looks like viewed from the outside. So many times they have these self-intersections on the inside. But we've worked on ways of converting from one to the other for many years, and we have a pretty robust system now. And we can do it very quickly too.
You need to get the 2.7 seconds.
Do you? Sorry?
It's relative. You put it as a conversion time.
Yes.
What is it running to?
Oh, what is it running on? Oh, right. This is running on an 8-core workstation. So it's definitely not a supercomputer. And it's of course multi-threaded. So the more cores you throw after it. We can also go, of course, the other way, which is given a volume, now let's go back to a mesh. Turns out most of our rendering code prefers meshes. And so what we have are what we call adaptive mesh extraction algorithms. So so you have very, very small voxels, but you don't want to introduce a triangle associated with every single voxel. That would completely kill the renderer. You get way too many polygons. So we have algorithms to produce adaptive tessellation. So when you have flat regions, you have very big triangles. And they're also pretty fast.
And that's also part of OpenVDB?
Yeah, it's all in there. We have techniques, I'll talk a little bit more about that, techniques to take point clouds and producing surfaces from it, which is a very typical problem we have in movie production. We have tools to filter volumes. So we can apply all kinds of filters volumetrically. So this is showing an example where we've smoothed away a corner. So we have a mask that makes sure only the red part is allowed to move. Everything else is static. We have what we call mathematical transformation. So we can produce gradient fields, mean curvature, Laplacians, magnitude, curls, all kinds of things. We've also used it for fracture. Fracture is surprisingly very difficult to do, especially when the model you have is not physical. So what we do is we take the models, convert them to a volume, and then we can do these things called CSE. It's basically Boolean operations. And we figured out a way to do it so the fracture seam is seamless. So when you render it, actually what you see on the left-hand side is already fractured, but you can't tell. So we pre-fracture, and then we sort of run an animation, and the thing starts splitting apart. So it's a complete cheat. Yes?
I think if the building actually was fracturing, like the
Oh.
showing, I don't know if it exactly fracture that. I mean, you could set up a scenario. I guess you have these physics rules you give, but I think that particular one you made some assumptions about structural strength being uniform through the building. Yeah.
It's a complete hack. There's nothing, there's no material.
Because if you're doing it as an engineer and
Oh yeah, yeah.
I don't think it would fracture that.
Oh, absolutely not.
You are solving, you said a friendly version of Navier-Stokes, but you're not solving
No.
kind of
No.
mechanical models.
Not at all.
Structural
And it's
models here. You're
and
not
that's
solving fracture, brutally nonlinear fracture equations that
Yes.
vary from material to material. And
right.
Okay, yeah.
And there are two very good reasons we don't do that. The obvious one, it's very slow. But there's even a more important one. Even if we could do it as efficiently as we can do this, we wouldn't use it. And that's because the artists want complete artistic control. They want to say, no, I want a fracture line right here. And that's actually the problem many times when we take physical equations, even like fluid equations, and we say, we know exactly how to simulate muscles or hair or cloth or water. And the director goes, no, I want that fire to look more angry. And you go, what? Right? So you can't actually use physics right out of the box. You have to cheat.
The physics engines are very important for the realistic
Yes,
elements. This is more of an animation where you
completely. Yeah, it's a complete hack. Water is probably one of the examples where we are the closest to the actual equations. But even there, we still do cheat. These are examples where I'm ray tracing some of the level set models. And we can, this is a level set. So left is a surface rendering. We can do in 300 milliseconds. And right is a volume rendering, where you have to shoot what's called secondary shadow rays. So it's a little bit slower, but it's still fairly fast. There's a guy, he's not actually working in my group, who wrote a OpenGL render for these that we use a lot. So we're actually rendering these VDB volumes in real time. And we can get very, very close to what we call finaling. So we can get approval. So the artist can sit and dial in the shader parameters, like for this, and the director will go, oh yeah, it looks great. And then he's like 90% within the final render. And the final render can take hours. So this is pretty nice. I just wanted to show you one quick example of how we're using this in production. So this is a very classical example. A lot of the fluid animations we do use a hybrid representation. They actually use both a grid and particles. It's something called flip. And the important thing is that the output is a cloud of particles. But obviously, you can't render a cloud of particles. It doesn't look like water. So the challenge is, how do you go from particles to something that looks like a water-air interface that you can actually render? And oftentimes, it's very, very challenging. It sounds easy, but it really isn't, because many times, the density of points is very low. Like, there may be missing points. But you still want something that's very crisp, very thin, has sharp features. So it's a much bigger challenge than you might think. And this shows actually the final result. And these are some of the operations that we are currently using, that we've sort of stitched it together, and the artists are now using this in production. So the idea is you're given particles, you take the particles and you turn them into a level set. That's very easy to do. You can just do spherical footprints. The problem, of course, is if you look at figure number 2, it doesn't look like water. It looks like cottage cheese. Then what we can do is we can take that surface and we can dilate it using some of these techniques I talked to about earlier. And then we can apply all kinds of filters. And then we can erode it to generate these very thin sheets. This is sort of an exaggerated example. This wouldn't actually be something in a shot. But what you have to realize is that we start out with very few particles, and we end up with something that is actually very thin, which is, as I said, it's quite difficult. Then we can do the adaptive meshing. So when we see the circulation is adapting to the we have big triangles where we have flat regions, and then all right, I think I'm just going to fast forward to the very last slide. Yeah, so it's not because I want you to see my thank you speech. In fact, I'm going to stop it before that. But it's kind of funny. At least we thought it was very funny. So this was, 3 weeks ago, or two and a half weeks ago. So when people thank the Academy, right, they actually thank the Academy of Arts and Sciences. So the Academy actually has 2 branches. And the arts is what they hand out the Oscars that you saw last weekend. The Sciences has another ceremony, which is separate, 2 weeks. Yeah, so we call it the Nerd Olympics. But it's fun. It's a real event. And Margot Robbie, who is a female lead in Wolf of Wall Street, was the host. And so, yeah, her introduction of our award I thought was pretty funny. I'm just going to play it.
Who wants to hear more about volumetric data? Yeah!
He's from
Miles does.
I love it.
You love that much
my
volumetric
favorite kind of data.
I thought it was. So that might be the case. Well, now that everyone can access the voxels and work with them, a team at DreamWorks Animation created an OpenVDB. OpenVDB is, I'm sorry.
That's so funny, Margot. It's just the name of the software.
I don't know why it sounds so sexual to me.
Yeah, right?
Get it together.
This is so immature. OpenVDB is available as open source. OpenVDB is available as open source software and provides a powerful tool set to process.
See, that's funny to me.
And manipulate the voxels, okay? To manipulate the voxels.
It's all about the voxels. Nice. Nice.
Yeah. Look. Yeah, all right.
Voxels, ladies and gentlemen, voxels, okay?
Yes, there we go. The open in OpenVDB is important. By making it available to everyone, it has become the state-of-the-art workflow choice for many studios, large and small. At DreamWorks Animation, the technology has been used most recently for How to Train Your Dragon 2.
Great movie. To Ken Museth, Peter Kuka, and Mihai Alden for the creation of OpenVDB, the Academy presents a Technical Achievement Award. Come on out!
All right. You can see the rest on YouTube if you want. No. You can go on YouTube. It's a sharp contrast to her, that's for sure. But yeah, that's, and I just wanted to thank a bunch of people, of course. Oops. Yeah, so Peter and Mihai, and actually David as well, They all worked on the open source release. And I shared the award with Peter and Mihai 2 weeks ago. And there's a bunch of people from DreamWorks, of course, and some of the other studios that we work with. So thanks for your attention.